Let's now look at a new component of attention called keys, queries, and values. So we looked at a sequence-to-sequence translation where we had an encoder RNN, then fed into a decoder RNN. And we said that the encoder RNN was going from, let's say, time steps 1 to T prime, and the decoder RNN was going from time steps 1 to T. And then we had hidden state here, hidden S sub j, and here hidden H sub I. And we use different letters just to try and distinguish the two RNNs, because otherwise it gets too confusing. As input, right, we have here our input at any given time step I is X sub I, and our input here at any time step, the important part as far as attention is concerned is that we have some context sub j. Right? And context sub j is a weighted average of all of the H sub i's. Why did we make it a weighted average? Why didn't we just choose the best H sub I? So when we're trying to output a particular word, for example, why don't we just look at the most appropriate word here? And the reason is this is what we might call a soft attention, right? So we have a combination of all of the H sub i's. And the major reason for that, there's two major reasons. So one is that way we can be attending to more than one word if we want. So we can pay most attention to one word, but secondary attention to some other word. The second important reason is that this is differentiable now, right? If we just had hard attention where we'd said, okay, context I is going to be 1, or context j is going to be 1 of the H sub i's, then we no longer can do backpropagation easily. Right here, the nice thing is we can make small changes to our weight matrices, and that will make small changes to our contexts. Whereas if we had a hard attention, we can make a small change to a weight matrix that would all of a sudden switch us from looking at one H sub I to a different H sub I, and that would no longer be differentiable. So we have this weighted average. The weights are alpha. I'm going to switch these to be X sub j and context sub I, and then these are H sub j and S sub I. So the weights are some alpha I sub j, and the alphas so the alpha ij's are generated from a softmax of the energy ij's across all j's. The way we looked at creating the energy was we had a one-level RNN, and we got out an energy, so a single value, and we fed in two things, right? We fed in S sub I, and we fed in H sub j. So these are the inputs. We go in the RNN, and we get the output. All right, so now is where we actually get to the keys, queries, values, because this is all just a review. We can have an alternative way, more efficient way of generating these energies. Everything else is going to stay the same. Once we generate the energies, we're going to go ahead and create a softmax. We're going to, from the softmax, we'll have these weights, and then from there we can go ahead and create a context, which is this blended, weighted set of our H sub j's. Okay, but we're going to just approach this somewhat differently. And let's look at a couple of just definitions here. When we look at H sub j, for instance, we're going to call that to be of size h. Okay, so it has h elements in it. When we look at S sub I, it's going to be of size s. And this, of course, could be different. So here's what we're going to do. Conceptually, what we're going to do is we're going to do something like this. So what we're going to do is, given a query, we're going to look for the closest keys, and we'll return a weighted sum of the associated values. We're going to have to define what we mean by all this, of course. So we're going to have a weight matrix that takes S's to queries. So when we multiply a particular S sub I by this weight matrix, we're going to come out with a Q sub I. And let's just look at these sizes. So S sub I is a 1 by size of S. WSQ is going to be something of size S by we're going to call Q of size D. And so Q is going to be 1 by D. Then we're going to also define keys as well. So we're going to have a weight matrix that takes H's to keys. If we multiply a particular H, we're going to get out an associated, so H sub J, we're going to get an associated K sub J. Again, let's look at the sizes. So this is a 1 by size of H. This is a size of H by D, where we're defining D. Right? D is just going to be the size of queries and keys, and the queries and keys have to be the same dimension. And so this is going to be a 1 by D. So it's important that queries and keys have the same dimension because we're trying to find the keys with that are closest to the query. So we want to be in the same D-dimensional space for that. All right. And then finally, we're going to go ahead and let's just define our values. Okay, so we're going to take H sub J by some W H sub V, and that's going to equal V sub J. Okay. Again, this is going to be 1 by H, H by size of V, and this is going to equal a 1 by size of V. Okay. So the values don't have to be of the same dimension as the queries and the keys. If WHV is just an identity matrix, then the value is the same thing as H sub J. And so when we went ahead and created our context, which is a weighted average of H sub i's, that's our assumption that our value is just the H sub J. But what this allows us to do is have a generalization that says our context isn't just raw weighted sums of hidden J's. Instead, it can be weighted sums of H's projected into some other dimensional space. Right? So it doesn't have to be a D-dimensional, it doesn't have to be an H-dimensional space, it can be some size of V-dimensional space. Right? So we can, in that way, perhaps shrink the H sub J's. If H sub J's are large, we can shrink them down smaller or larger, or whatever we want to do. Right? But we're going to still look at how we can compute these energies. And the way we're going to compute the energy is like this. Okay, we are going to basically take Q sub I and K sub J transpose. So this is going to be a 1 by D, and Kj transpose is going to be a D by 1. And so this gives us the energy for I comma j. And this again is a 1 by 1. Just as we could feed S sub I and H sub j into this one-level neural network and get out our energy, we can alternatively feed S sub I through this matrix to get a query, H sub j through this matrix to get a key, and then do this matrix multiplication and finally get our energy. So it's a different approach we're using, but again, we're effectively taking Si and Hj and feeding to get an energy. The difference is what would be learned here. Instead of learning the weights of this neural network, we're learning the weights of these two weight matrices.
This multiplication of Qi and Kj transpose is just calculating the dot product of Qi and Kj. That's a good measure of how similar Qi and Kj are. So the more similar they are, the higher that dot product is going to be.
Why is this any better than this? Well, the advantage is scaling. So in this one-level neural network case, we have got to do this one-level neural network for all of our H sub j's independently. What we can do instead is go ahead and use matrix multiplication and actually calculate all the energies for all the keys for a particular query simultaneously. So let's look at how we can do that. So what we can do is, instead of just taking K sub j, which is a single key, we're going to take the whole collection of the keys for all of the h's. We are going to have K1 all the way through Kj. t prime. And that is what we're going to call k. So k consists of the 1 by d for k1, the 1 by d for k2, all the way to 1 by d for kt prime. And what's the size of this? This is t prime by d. So what we note is if we take qi times k transpose, again, looking at the sizes here, this is a 1 by d. So let's go ahead and fix this. D is, of course, a constant. It's not a size. And this is a d by 1. Here we have a 1 by d and a d by t prime. So we're going to end up with energy I1 all the way to energy I t prime. So we've got all of those energies in a single matrix multiply. If we now go ahead and do a softmax, then we have all of our alphas. And again, this is the size 1 at t prime. So this gives us all of our alphas. And now we can go ahead and do our computation of our context, right? We can just say that the context, so let's look at V for a second. So V is going to be equal V1 all the way to Vt prime. And again, I'll remind you, if this is an identity matrix, then our V's are just our H's. But in any case, what we can do now is multiply this by V. Okay, so we'll take this amount of the first V1 and then alpha I2 times V2 all the way to alpha IT prime times Vt prime, and that will give our weighted sum. So our final calculation we can do is we take the softmax of Qi kt, and then we multiply that by V. And what's that going to be? That's context sub I. And let's just fix this too. Over here, right, context sub I is a weighted average of the H sub j's. The weights are alpha ij. Okay. So what's the advantage of this? The advantage of this is, so once we've calculated Q sub I, calculated K, calculated V, then we can just do this large matrix multiplication and get out, basically do this computation and get a particular context. So this is a transpose, a matrix multiply, a softmax, another matrix multiply. And of course, GPUs are ideally suited for doing these large matrix multiplies. There's more though, right? And that is, this gave us, in these two matrix multiplies, a single context. We can actually, by doing two matrix multiplies, get all the contexts. Okay? Now, this is a case, as we're talking about the decoder RNN, this doesn't make a lot of sense because of the fact that we're generating our context one by one, right, dependent on our previous states. But let's say, just for the sake of example, that we didn't have a decoder RNN here. We just had a situation where we had a bunch of S sub i's, and we want to get the context for each of those S sub i's simultaneously. So what would we need to do? So what we would do is we would calculate Q. So Q is going to equal WSQ, and we'll just multiply by all of our S sub i's. So S sub 1 all the way to S sub t. And that's going to give us Q, which is going to look like Q1 all the way to Qt. And again, just checking, what's the size of this? This is going to be T by size of S. This is size of S by D. So this is going to be T by D. And our keys are T prime by D. And then here's what we do. All we do is we take softmax of, instead of Qi times KT, just take Q times KT, K transpose, right? And then we'll multiply this by D. Let's just look at what's happening. Q is a T by S. Sorry, Q is a T by D. K transpose is a D by 1. Sorry, this K transpose is now D by T prime. So we've got this Q times transpose of K, and that's going to give us something of size T by T prime. So really what that's going to be is the entire energy matrix for all possible i's and j's inside T and T prime. We can take the softmax, that gives us our alphas, and then we can go ahead and do this weighted sum of these. So what we're going to end up with is a bunch of context. Context 1 all the way to context T. So in one fell swoop, we can get all of the context as necessary. And so that is how keys-queries and values work. Again, a reminder that the value can be just the h's incoming, right? Can just basically be the keys. That would be what this is in this case, right? So the values can be the keys, the values can be the h's, or the values can be really anything we want because we have this extra weight matrix here. And we're going to go ahead and let our neural net, once we set this all up, kind of learn what all of these weights are going to be. We're going to have to decide how big we want D to be, so how long the queries and the keys are, and we get to decide how long the values are. That's basically keys, queries, and values.